Let's look at an application example, signal energy and image classification. In this application, we first show how signals energy can be used to organize a set of night and day images into two different classes, and then we use a more sophisticated classification method. If we use an example data set containing labeled images of day and night, we can create a simple classifier by using signals energy as the distinguishing image feature between the two groups of images. Since the images are not uniform in size, we normalize the signal's energy by dividing it by the number of image pixels. Strictly speaking, this returns the signal's power. Now let's find a threshold that is the average of the mean energy of the night images and the day images. Signal's energy or power is a very simple image feature to use as a classifier, but it also does a decent job of separating the example images. Let's apply the computed threshold to a number of unclassified images. As shown here, our method failed to correctly classify one of the night images. There are more advanced classification techniques that are built into the Wolfram language, which are more advanced. For example, nearest neighbor regression, decision tree, support vector machines, or neural networks. Here we use the function classify to classify our day and night example set. The function classify combines several classification methods and implement a high-level automation around them to perform classification using the most suitable method available. Now let's try this classifier on our test images. Not unexpectedly, one of the images is misclassified. In this application, we saw how we can classify and organize a set of night and day images using the signal energy of the images. We tried two different methods, first by defining a classification threshold and applying the threshold to the set of images, and then we tried more advanced classification methods using the built-in functionality in the Wolfram language.